everyone. I'm Oleg, and I'll be there as tech support during the tutorial. I want to introduce you to our tutor, Vladimir Kovacevic. He's a teaching associate at Faculty of Sciences, University of Novi Sad, and he will hold the deep learning techniques for monocular depth estimation tutorial. Enjoy.
Okay, hi everyone. Let me just share a screen. Do I need to turn on camera?
You can if you
Okay,
like.
I'll just turn it on for a moment just to say hi everyone, and I will share a screen now. Now, do you see my screen? Can you see my screen?
Yes, we can see.
Okay, let us start then. Okay, hi everyone, and welcome from my welcome from my side also. Come back, something is not working. Okay, welcome to data science conference from my side also. Well, since you introduced me, I don't need to repeat myself. I'll just say that you can have you have here a link for my LinkedIn account, so feel free to connect if you like. Okay, so the plan for today is to talk about 3 papers from first 3 bullets. So those 3 papers, we will comment on some recent work from this year, from 2023, where I will refer you to read that paper. At the end, I will give you homework in form of Colab notebook, where you need to fill some to-dos in order to make your first depth estimation model. Now, the idea with this tutorial is to give you a different perspectives to solutions of the same problem. I will try to present 3 of our 4 approaches for monocular depth estimation and show you how you can load and use trained networks. I won't go deep into experimental results and evaluation of each approach, but I will refer you to all papers I use for this presentation, so you can, if you want, to dive into those really important stuff. What is monocular depth estimation? Well, as the name says, monocular depth estimation is the task where for a given single picture, we need to predict depth of every pixel, each pixel on it. To understand how difficult it is, you can, if you like, try to close one eye and put your index fingers opposed to each other, and then position them such that when you move them to each other, their tips touch. The chances are that you won't be able to do that. Okay, so the first paper has this title, High Quality Monocular Depth Estimation via Transfer Learning. Before we dive into this paper, let us deeply understand what is monocular depth estimation. Okay, human vision perceives depth effortlessly, but for machines, estimating depth from a single image, a process called monocular depth estimation poses significant challenges. And as we saw from this little experiment few moments ago, if you close one eye, you also have trouble to estimate depth. So human can perceive depth effortlessly because we have we can see spatially since we have 2 eyes. Why it's hard for computers? Well, unlike stereoscopic methods that can mimic human binocular vision, monocular cues are subtle and less pronounced, making that depth estimation complex. Also, if you look at it mathematically, if you imagine 3D space and some ball centered around z-axis, and if you move it up and down along z-axis, well, the projection on xy plane is always the same. Also, you can have all sorts of problems on your images. For example, here reflective materials or different lighting conditions and things like that. But why is monocular depth estimation important? Well, depth perception is critical for numerous applications such as autonomous driving, 3D reconstructions, robotics, and augmented reality. Okay, now more formally, depth estimation requires predicting a continuous value for each pixel in the image, representing the distance from the camera.
Since regression is the task of predicting continuous outcomes, it is only natural to pose problem like that, like regression problem. The goal is to produce a depth map where each pixel contains a depth value. This is so-called a dense prediction task, meaning that we want to predict an output for every input pixel. A regression approach allows for each pixel depth to be predicted individually, but in a spatially coherent manner. And that's why it is natural to seek for help from convolutional nature of convolutional neural networks. Now, semantic segmentation is also a dense prediction task, and that's why we can use methods developed for semantic segmentation. For example, UNet-like architectures to try to solve the different but somehow connected problem of depth estimation. Okay, depth values in real-world scenes are typically smooth and exhibit spatial correlation, except at object boundaries or discontinuity. Regression methods, especially with convolutional layers, can capture this spatial correlation up to some extent. Here you can see the example from one data set. So you have image depth pair. This is a ground truth, at least for our model. And this predicted depth is done using the homework model that I will show you at the end. So this is the kind of a motivation that you can build a pretty simple model using that notebook I will refer you to make some meaningful results, but we'll come to that later. Okay, about loss function. Well, regression problems in CNNs are typically approached using loss functions like mean square error, mean absolute error, or smooth L1 loss that are well suited for difference between the predicted and ground truth depths. We will see a loss function used in this paper later. Now, why transfer learning for monocular depth estimation? Well, the reason for that is general reason why we use transfer learning. Well, we here also we have limited depth data, so we have scarcity and high cost of obtaining labeled data sets from depth estimation. Also, using the transfer learning, we can learn from abundance, right? Transfer learning exploits large data sets from related domains to enhance performance on depth estimation. Also, features learned by models on large data sets can be universal and beneficial for depth-related tasks. Just a short background. Before deep learning, people used all kinds of methods. Here are just few of them: defocus, blur analysis, structure light, motion parallax, heuristics, of course, heuristics everywhere, semantic analysis, and things like that. And now, in the rise of deep learning, well, we transitioned to the deep learning era where CNNs began to outperform traditional methods. And also, transfer learning is a breakthrough that allows leveraging pre-trained networks on large data sets to boost performance in depth estimation tasks. Okay, here are some bullets regarding results of the paper. Well, the authors made simple transfer learning based network with high accuracy and quality. They introduced loss function tailored for monocular depth estimation. That maps capture object boundaries more faithfully than before. Concretely, they used UNet-like architecture, which was originally designed for semantic segmentation. But both those tasks are dense prediction tasks. Okay, they showed some performance improvement. They achieved at that time state-of-the-art results on standard benchmarks, quantifying improvements over previous methods. Also, they showed robustness and generalization. Namely, they demonstrated the model's robustness and generalization across diverse scenarios not covered by the training data. Concretely, on this Unreal 1K dataset, Unreal, you can find it online, is Unreal Marketplace, the dataset. Okay, now to justify that this is a transfer learning approach, well, the encoder is DenseNet 169 pre-trained on ImageNet, which is first few lines of table here. So it's encoder, bullet encoder here, and then encoder ends here. So this is an encoder. Okay, and then decoder starts with 1x1 convolutional layer with the same number of output channel as the output of a truncated densenet. You can see that here. Then we have upsampling blocks, each composed of 2 times bilinear upsampling followed by 3x3 convolutional layers. This one here. With output filters set to half the number of input filters, and where the first convolutional layer of 2 is applied on the concatenation of the output of the previous layers and the pooling layer from the encoder. So of course, having the same spatial dimension, meaning that we also have skip connections like the true UNet architecture. Okay, then each upsampling block, except for the last one, is followed by a leaky ReLU activation with alpha 0.2. Alpha is slope for x smaller than 0 for a ReLU function. Okay, a loss function can have a significant effect of training speed and the overall depth estimation performance. The proposed loss in this paper finds balance between reconstructing depth images by minimizing the difference of the depth values while also penalizing distortions of high frequency details in the image domain of the depth map, which are typically boundaries of the object, as we saw in the slide before, where we had the bed and then boundaries of the bed, for example. Okay, a loss here is composed as weighted sum of 3 losses. First part is the standard L1 loss. You can see it here. So YP and YP hat are prediction and ground truth for each pixel. So it is done pixel-wise. Lambda is, I think, 0.1, so it doesn't affect learning as much as other two. Second part is also L1 loss, yes, but over the image gradients of that image. Okay, you can see that here GX1 and GX2 are image gradients over the horizontal and vertical axis of the image. The third part uses a structural similarity term. Just at a high level, the structural similarity is a method. Index is a method for measuring the similarity between two images. It compares local patterns of pixel intensities, providing a more accurate and human vision aligned way of measuring image quality and traditional method, like, for example, mean square error. Okay. Here are some implementation details. Well, the authors use data augmentation, and the reason for that is because the data sets for depth estimation at that time were really sparse. We didn't have much data. So one way to artificially add data is, of course, data augmentation. But you always have a question. Does it make sense to do every augmentation? For example, does it make sense to do vertical flipping? So you can you swap ceiling and floor? Well, probably not, because geometry of ceiling and floor are not the same, right? But it does make sense to do horizontal flipping or mirroring with coin flip probability. Also, authors did red and green channel swapping with probability 0.25. They implemented their network in TensorFlow. Later, they added PyTorch implementation. Okay, they trained it on NVIDIA Titan. Never mind, it's not so important for us here. The hyperparameters that is important, so they used optimizer Adam with learning rate 10 to the power of -4, right? With beta 1 and beta 2, I think those are actually the default parameters for Adam. They control the first and second momentum, so the mean and variance for this optimizer. They use batch size of 8. Final model had 42 million parameters, and they trained for 1 million iterations for this data set and 300,000 iterations for this data set. Now, on the right, you can see a high-level overview of architecture. So you have encoder, pre-trained dense net 169, the customized decoder that they introduced, and some skip connections here. Okay, about datasets. Well, I'm sorry. Well, the first dataset was NYU depth. That is a dataset of indoor scenes at resolution 640 by 480. They used 50,000 training samples out of 120,000 samples. The depth upper bound for that dataset was 10 meters, and the data was gathered using Microsoft Kinect. The other one is the Kitty, and this is some abbreviation. I forgot what it was. It's something Toyota Technology Institute and something here. Never mind. That data set contains stereo images of outdoor scenes at resolutions at this resolution. They used 26,000 training samples from that data set, and that data set has upper bound for depth. Okay, that data set has depth upper bound 80 meters. The data was gathered using moving vehicles, so that's the reason why the images are that wide. Okay, now I would like to go to Google Colab. Do you see my drive here?
Yes, we can see it.
Oh, thank you. Okay, so we can go to this folder here. This is a dense depth model. In that folder, you have pre-trained weights you downloaded from official GitHub of this implementation, and some utils function that if you're a newbie here, you don't have to worry about, but if you want, you can download it and go through it offline. Okay, this model is around 4 years old. So Python has changed a lot since then. So I had some problems to load this model. But if you use this notebook, I suppose you won't have a problem loading this model. Concretely, this model has some custom layer bilinear upsampling, and also it utilizes the normalized tuple function that is now deprecated. So I had to find that old implementation. But never mind, I have incorporated all relevant components into this util.py, so you can directly use the model with just few lines of code. Here we just load some dependencies. Okay, here you can load your drive or my drive here, since you have access to this folder. You load the bilinear upsampling custom layer and the predict function downloaded and tweaked from GitHub, from official GitHub. Okay, you load your model. I'm not sure if you saw this earlier. So if your model or someone else's model has some custom object like here custom layer, then you have to specify for the keras that your model has some custom object, and we do that here. Okay, this is some utility to load and predict and to plot our depth images. And here are 4 images from test data set of NYU depth data. So you can see this model does have kind of blurry results, but it does capture object boundaries. And that is because it uses some custom loss function that we saw earlier. Okay, maybe this picture here you can remember if you like that here we have some boundaries in this chair here, and the model didn't recognize that also here. This is some random online image of some bridge, and you can see that model got confused with this image. For example, I think that it got confused also with this shadow here, so everything is blurry, but you can see boundaries of the bridge. Here you can't see this tree, for example, and you can't see anything anything of this forest here. And those three pictures, those three are actually generated by ChatGPT. So the model actually does fine job here, but for example, here you can see that we have boundaries of the two different buildings, and the model didn't recognize that here. This image is quite complicated because it has quite a lot of details. So the model did fine job. I mean, you can see some that it gave a blurry outcome, but it did a fine job. Okay, it got confused here maybe. This thing should be the forest, but it didn't recognize. Okay, and this is some weird image generated by ChatGPT. So it's some kind of a room in a desert, I think. And yeah, model got completely confused here, so it didn't recognize much of the details here. Okay. Come back. Oh, okay. Okay, the next paper is Adabin's paper, or Adabin's paper. I will call it Adabin's because it's natural for me. It's called the Adabin's depth estimation using adaptive bins. Just a side comment, those two folks are actually the authors of the previous paper, so we have one new folk here. Okay, well, transfer learning has changed the way we approach machine learning problems by leveraging pre-trained models to achieve better performance with less data on a new but somehow related task. However, transfer learning, of course, is not without its limitation. It often requires large computational resources for training and might not always capture the best nuances of that. Moreover, the performance of transfer learning models can be constrained by the diversity and size of source data set. Of course, every data set comes with its own biases. And with that context in mind, we will explore Adabin's an approach that innovates beyond transfer learning, let's say. Okay, well, what does Adabin stand for? Well, it stands for adaptive bins, which is, since it uses a transformative approach in the sense we tailor the depth estimation process more precisely than before. Along with the ill-posed nature of the problem, as we talked earlier, depth estimation corresponding to a different RGB inputs, of course, can vary to a large extent, which makes depth estimation even more challenging. The core idea behind Adabins is to move away from fixed-size depth bins, which have been a common practice in depth learning, in depth estimation tasks. Adabins dynamically adjust the size of the bins according to the scene's context. The adaptability allows for more accurate depth estimation, especially in areas with subtle depth changes. I mean, you can see that from the results of the paper, which we won't comment on here. Traditional depth estimation often relies on bins of uniform size, which can be likened to trying to measure every room in a house with the same sized yardstick. On the other hand, Adabins introduces a custom fit measuring tape for each room, significantly enhancing the model stability to discern fine details and various in depth. And now the question is, to bin or not to bin? Well, of course, to bin. But how is binning applied? Well, binning is applied to the range of possible depths that the model can predict. Notice, not to the spatial layout of the image itself. We will see that idea later in the third paper. The image remains a whole, and the bins are conceptual divisions of the image dimension. Each bin represents a range of depth values. For example, one bin might represent depths from 1 to 4 meters, and then another one from 4 to 5 meters. So the first one probably has some I don't know, sky or something like that. And here we have greater details, for example, some forest or something like that. And each bin has a center value, which is a representative depth for that bin. The center value is used in the linear combination to estimate the depth of each pixel in the image. And why are they important? Well, the center values is used in the linear combination to estimate the depth of each pixel in the image. During the depth estimation process, each pixel in the same image is associated with these bins in a probabilistic manner. Of course, it is not completely stochastic or some kind of chaos. The model predicts a distribution over these bins for each pixel, indicating how likely it is for the pixel to belong to each depth range. And the final depth prediction for each pixel is then computed as weighted average of bin centers. So here you can see some examples from paper, the original image, and the obtained depth using other bins. Okay. Now, other bins introduces several key innovations to the field of monocular depth estimation. First, the adaptive binning mechanism revolutionizes how we approach the problem of discretizing depth. Instead of predefining bin sizes, which may not suit every scene, other bins dynamically adjust bin sizes during inference, allowing, of course, for more precise depth predictions tailored to each unique image. Namely, the motivation for this work is different paper that can be found in other bins paper, and is idea to transform regression task into a classification task. However, they propose to divide the depth range into a fixed number of bins of a predetermined width. In other bins approach, authors found sweet spot between classification and depth map regression with dynamical binning and in a way that bin widths are adaptively computed for each image. And you can see that illustration of that here. So for two different images, you have completely different bins. So bins are bin centers represent different depth ranges. Okay. Also, it is worth emphasizing the discretization of depth interval in a way that each pixel is assigned to a single bin would lead to discretization legacies. That is why the final depth estimation is a linear combination of the bin center values. Essentially, this means that depth value of each pixel is computed as a weighted sum of the bin center values. Another important thing is that the high-level view of the architecture is encoder, decoder, and then attention mechanism rather than encoder, attention, decoder. Why? Well, because authors notice that the attention achieves better result when applied to spatially higher resolution tensor. So here, in encoder decoder architecture, this is a bottleneck. Okay, so the encoder decoder part is similar as one we discussed in the previous paper, with the difference in pre-trained encoder. So encoder is not the same as previously. Now is efficient net B5. And why? Well, because it is a smaller, so they can concentrate on other bins module here. But also they use different loss function. The adaptive bin width estimator is one that we concentrate on here. So we don't care here about encoder decoder. Okay. Now, this MVIT is mini vision transformer, and it is enlarged here. Now we will try, or I will try to explain it. So output of the decoder is a tensor X, this one. Those small h and small w are half of the input resolution. Then a vector is fed to this MVIT module here. It has two outputs. First one is the vector B, and that is a vector of bin widths, which defines how depth interval is to be divided for the input image, and is calculated using global attention. Vector X is passed through a convolutional block called embedding call. So this one here, with kernel size P by P and stride P, where P is a patch size, and you can see in MVIT specification it's set to be 16. Okay, the result, okay, that this embedding conv results with tensor of size h divided by p times w divided by p times e is the number of output channels. That vector is then fed is reshaped into a s times c, where s is obviously h times w divided by p squared. And that serves as effective sequence length for this transformer. Okay, that sequence is e-dimensional vector, which is on figure called patch embedding. So this thing here, patch embeddings. The output of the small transformer is sequence of output embeddings, also from RS times E. Then the MLP head, MLP is a multi-layer perceptron. Head is used over the first output embedding, and it uses ReLU activation and outputs n-dimensional vector. Here it's not specified, but in GitHub implementation you can see that this n is actually 256 also. Okay, that is then normalized such that it sums to 1 to obtain the final bin width vector b using this formula. Here, epsilon just ensures that all bin widths are positive. Also, the idea with this normalization is to introduce, let's say, a competition among the bin widths and to force network to focus on subintervals by predicting smaller bin widths at interesting regions of interval. And that is about this part here. So the first output. The second output is R, this range attention map of size h times w times c that contains pixel level information. Okay, let's start over. The decoder features represent a high resolution and local pixel level information, while the transformer output embeddings contain global information. What is happening then here is equivalent to, let's say, calculating the dot product of the attention weights between pixel-wise features treated as keys and transformer output embeddings treated as queries. So to explain, the model treats features extracted from each pixel of the input image as keys. These keys represent the unique characteristics of attribute of each pixel. The output embedding from the transformer model are treated as queries. The queries are used to seek out relevant information from the keys. Then the model calculates the attention weights by performing a dot product between these keys and queries. This process essentially evaluates how much attention or importance should be given to each pixel's feature when considering a particular transformer output embedding. Such design of using output embeddings as convolutional kernels lets the network integrate adaptive global information from the transformer into local information of the decoded features. Okay, that is R. Now next, so we have R and B. Next, range attention maps are passed to 1x1 convolutional layer here. In order to obtain n channels for each pixel. That is followed by softmax activation to be interpreted as n probabilities pk over n that bin centers C of B. Okay, you can see that here. So C of B is a vector containing the elements calculated using this formula here. Finally, the depth prediction is then calculated just as a dot product of C of B, and P. This vector P is a vector containing all pk probability distributions. We should note that depth is not predicted as being center of the most likely bin, so it's not hardly discretized. It is rather calculated as sum of all bins weighted with corresponding probabilities here. So probabilities here are serves as some kind of weights.
Okay, and then the final depth map is again computed by bilinear upsampling to the same resolution as input. So here we have half of resolution, and then we have few more layers to bilinearly upsample to the same resolution as we started with. Okay, the loss function, well, you can see it here. Let me just briefly explain it, because it would be a different topic if we go deeper in there. First term, this one here, scale invariant loss, is designed to be invariant to the global scale of the depth, which is crucial because the absolute scale of depth can be difficult to determine from a single image. The loss is calculated based on the logarithmic difference here between the predicted depth and ground truth depth. Now, this transformation is important because the depth perception is often logarithmic in nature, meaning that we are more sensitive to changes in depth when objects are closer. And with logarithmic transformation or logarithmic function, we can model that. Second term, let's say this one, transfer loss, let's say encourages the distribution of bin centers to follow the distribution of depth values in ground truth, since we would like to encourage the bin centers to be close to the actual ground truth depth values. Okay, so this use of transformer-based architecture, let's say, marks a departure from convolutional approach typically seen in depth estimation. This architecture leverages self-attention mechanisms which are particularly adept at capturing global dependencies in data, an essential feature, of course, for understanding complex scenes. This is the way to overcome drawback of convolutional layers, where they only process global information once the tensor reach a very low spatial resolution at or near the bottleneck. Generally, idea here is to perform a global statistical analysis of the output of encoder-decoder architecture, and also to refine the output with learned post-processing building blocks. Okay, about implementation details. Encoder, as we said before, is efficient net B5. Decoder is standard, nothing special here. The attention is important here. So it's Adabin's model. It was implemented in PyTorch. They use different optimizer, Adam W, with weight decay 0.01. They trained only for 25 epochs, used batch size 16. And the final model had 78 million parameters. And you can see the Adabin's model. So this one here had only 5.8 million parameters. Okay, now we can go to Colab. Let me just open it. Adabin's. Okay, you have Adabin's weights downloaded from official implementation, and you have see here some code that I wrote for you. Right. Okay, here this is a more recent one than the paper before, so I managed to clone GitHub and use much of a code from their original implementation, so we don't have to care about those details. Okay, I followed the prescribed procedure. The procedure prescribed by the authors on GitHub. So we copy our weights to this folder. We first make that folder, and then we use their models, and from that module we import unit adaptive bins. Okay, we can specify a number of bins. I didn't change this. This is from official implementation, and here we can use this inference helper. The inference helper just abstracts away, let's say, boring stuff from us, like image pre-processing, post-processing, and things like that. We don't have freezing the layers and things like that. Putting the model in evaluation phase and similar things.
So we don't have to worry about those details. Here we just write some code for prediction and plotting. And here, actually, the point here is to see this distribution of depth bin centers. So, for example, for this image, we have one depth distribution, and then for different image, we have a different distribution. You can actually see here that we have more higher bins because we have more pixels that are far away from the camera. Okay, here you can, if you remember from the first one, here you can see that other bins actually capture the boundaries of this chair here, and also up to some extent here. Okay, it got a bit confused with this bridge, but it's definitely much better than the first model. Here are the ChatGPT photos, or not photos, images. Okay, it got confused here, fair enough. And it got really confused here. Okay, I don't have anything to say more here. Let me just take a 30-second break to have some water. Okay, let's continue. Oh yeah, I forgot to just to comment. The transfer learning approach often relies on fixed size bins. As I said before, other bins challenges this by introducing an adaptive binning strategy, which creates bins of varying sizes based on the scene's content, allowing for a much finer depth resolution where it's needed the most. While the transfer learning methods we looked at were largely convolutional, AdaBeans employs a transformer-based architecture. This shift allows AdaBeans to better capture the global context of the image, an important aspect for understanding complex depth relationships. Okay, here quantitatively, AdaBeans achieve superior performance. AdaBeans achieve superior performance metrics over traditional methods. This include lower error rates and higher accuracy in standard metrics such as absolute relative error, squared relative error, and root mean square error, and things like that. Quantitatively, visual comparison of depth maps reveal that AdaBeans can capture depth information with higher fidelity and faithfulness. Edges are more distinct, object boundaries are clearer, and gradual depth changes are more smoothly represented. You can see that here, this is a ground truth, and this is a AdaBeans model, and these are some state of the art at that time. I forgot the names of those models. Okay, now we can go to something different. Okay, the third paper here is vision transformers for dense predictions. This is a completely new idea, and I tried when I chose those papers to have somehow connected first and second one, and now the second one and the third one. So there, if you remember, we had mini VIT. Now here we will have VIT, actual VIT. So, but in order to compare VIT approach to convolutional neural networks approach, let's have another overview of CNN approach. Those architecture usually resemble encoder-decoder architecture, as we saw, where the encoder is pre-trained on image classification tasks. Also, as we saw, then decoder aggregates features from encoder and converts them to the final dense prediction. Encoder downsamples input images in order to extract features. As we go deeper with downsampling, we obtain capacity for receptive field. I mean, that's the nature of convolutional neural networks. On the other hand, we pay price in feature resolution, which leads, as you will see in the exercise, I'll show you again at the homework. And if I forget to say, please remind me. Okay, so that leads to problem in recovering features in the decoder. This is not problem is for example, image classification task, because we have at the output some n-dimensional vector with probabilities, and that n is much smaller than original image resolution. So, but here, however, here is a crucial to resemble the original resolution for the input image as much as possible. As we saw in the other bins, they did. I think they resembled the whole resolution. Yeah, they did resemble the whole resolution of the input image. Okay. Although there are different strategies to overcome this problem with CNNs, those networks are bottlenecked with their fundamental building block, which is a convolution. And as the authors say in the paper, convolution by definition is linear operation, and it has a limited receptive field, as we said before. The limited receptive field and the limited expressivity of an individual convolution necessitates sequential stacking into very deep architecture to acquire sufficiently broad context and sufficiently high representational power. This, however, requires the production of many intermediate representations that require a large amount of memory. Downsampling the intermediate representation is necessary to keep memory consumption level at that are feasible with existing computer architecture. So we have a war here and we don't have a winner. And now for something completely different. So the authors of this paper, Vision Transformers for Dense Predictions, introduce Dense Prediction Transformer, or DPT. It is also based on encoder-decoder, but it leverages the transformer as the building block of the encoder. They use the Vision Transformers, or shortly VIT, introduced in paper and images worth 16 by 16 words by Google Brain Research. And I will reference you to that paper if you want. It's worth reading. It will be reference 5 at the end. Okay. This involves transforming VIT bag of words output into image-like features at various scales. These features are then progressively fused into the final dense predictions through a convolutional decoder. Unlike a fully convolutional network, this VIT-based approach doesn't use frequent downsampling after the initial image embedding, maintaining constant dimensionality throughout the process. This approach provides a global receptive field at each stage. They demonstrate that these characteristics are particularly beneficial for dense prediction tasks, as they enable detailed and globally consistent predictions. Okay. Oh, I forgot to change slides. Okay, now about architecture. So the Vision Transformer functions by treating an image as a collection of quote-unquote words, similar to a bag of words approach. In this context, segments of the images are considered the equivalent of words. These are referred to as tokens in paper. The transformer architecture then processes these tokens through a series of building of blocks that utilize multi-headed self-attention, or MHSA. This process allows each token to interact with each other, thereby transforming their collective representation. Now, for our purposes, it is key to note that transformer consistently preserves the number of tokens during its operations. Since there is a direct correlation between tokens and image patches, this implies that the spatial resolution of the initial embedding is maintained throughout all stages of the Vision Transformer encoder. Moreover, the multi-headed self-attention mechanism used which was used is global by nature, allowing each token to interact with and influence every other token. As a result, the transformer exhibits a global receptive field at every stage following the initial embedding. This approach differs from convolutional networks, where the receptive field gradually expands through successive layers of convolution and downsampling. Just a side comment here on multi-headed self-attention, that is the network, let's say, to simultaneously focus on different parts of the input sequence to understand its context better. Each head, quote unquote, in this system can attend to different aspects of the image, enabling the model to capture complex relationships with the data more effectively. And to cite the paper here, VAT extracts a patch embedding from the image by processing all non-overlapping square patches of size p square. Okay, so here we have image, and then we made patches of that image. We made p squared patches. The patches are flattened into the vector and individually embedded using a linear projection here. Since transformers are set-to-set functions, they do not intrinsically retain the information of the spatial position of individual token. The image embeddings are thus concatenated with a learnable position embedding to add this information to the representation. Following the work in natural language processing, the VAT additionally adds a special token that is not grounded in the input image, and it serves as the final global image representation. You can see it here, so it's this, let's say, red one. We refer to special token as the readout token, and the result of applying the embedding procedure to an image of size h times w pixel is a set of tokens. So this set of tokens here, where the zeroth is a readout token, this red here, and other NP tokens are actually a representation of that image. So each and every element of this set is in RD, where D is a feature dimension, and we have NP of those. So H is the height of the image, W is a width, and P square is a number of patches here. Okay, then, so we have this here. Then the input tokens are transformed using L transformers, this one here, into the new representation. Authors were using 3 variants of VAT from mentioned and images worth 16 by 16 words paper, but I won't go deeper into this part because, yeah, that would be also a topic on its own. So I'll just name them. They used VAT base, VAT hybrid, and VAT large. Okay. Now is the time to decode and assemble set of tokens into an image-like feature representation, because at the output we want to have something, some image. Okay, convolutional decoder does that at various resolutions. Those representations are progressively fused into the final dense predictions. Authors proposed for that reassembling to be done in 3 stages. And you can see those stages here, and it's written here. So resample, concatenate, and read. Actually, first read, concatenate, and then resample. Read serves to appropriately handle this readout token, which can be useful to capture global information. So there are 3 variants from paper for these read functions, and they are written here. First one just ignores a readout token. I mean, that can be fair, since it is not directly relevant for dense predictions, but since it can capture global information, maybe this approach is not the best one. The second one passes this information from a readout token to all other tokens, just simply adding adds it to them, to all others token. Okay, and the third concatenates readout token to the others. So here we just concatenate T0 to every other, and then we we apply MLP, so multi-layer perceptron here. I didn't find how exactly this MLP looked. Okay, then after reading that token or handling the readout token, concatenate function serves a purpose to reshape this NP tokens into an image-like representation. So this is where the magic happens. It uses information of initial patch position to place each token according to those positions. So you can see that transformation here. Okay, first we just have from RNP plus 1 times D to RN NP times D, and then we have something that looks like an image using this concatenate function. Then resample function spatially resamples representation with few convolutional layers. Okay, this reassembling procedure is done at 4 different stages and resolutions, as you can see here. So reassembling is done from deeper layers of transformer of lower resolution. So here, for example, as well as at higher resolutions, for example, here. Those extracted features, so we are here now, after reassembling function, those extracted features are combined using refined net based feature fusion block here, or you can see it magnified here. Upsampling is done progressively by a factor of 2 at each fusion stage. Final representation size has half the resolution of the input image. Then output monocular depth estimation head progressively, this one here, MDA head, progressively upsamples the predictions with bilinear interpolation to the input resolution. Okay. Just a side comment, the dense prediction transformer can handle different image sizes as long as the image size is divisible by this number P. Okay, let's just describe it again at a higher overview. So the input image is transformed into tokens, so those orange or yellow things here, either by extracting non-overlapping patches followed by linear projections of their flattened representation. That is done for DPT base and DPT large, or by applying a ResNet 50 feature extractor for DPT hybrid. Then the image embedding is augmented with a positional embedding and a patch embedding readout token. So this red or orange token here. Okay, then tokens are passed through multiple transformer stages. Here, we reassemble tokens from different stages. So here. And then we obtain image-like representation and at multiple resolutions. Then fusion models here, or magnified here, progressively fuse and upsample the representation to generate fine-grained predictions. Okay, here at the center we have overview of this reassemble block or reassemble operation. Tokens are assembled into feature maps here. Okay, and then on the right, here we have fusion blocks, combined features using residual convolutional unit and upsample the feature map. So you can see the residual convolutional unit here. Okay, for the training, they use combination of losses, which I will try to explain just conceptually. So they used so-called scale and shift invariant trimmed loss. This loss function operates on inverse depth representation. The inverse depth representation is a method where depth is inversely proportional to the image, meaning closer objects have higher values. The scale and shift invariant aspect implies that the loss function remains effective regardless of the scaling or shifting the depth values, accommodating variations in absolute depth scales across different images. Also so that's first part of loss, and then the second part of the loss was so-called gradient matching loss. This loss focuses on the gradients or changes in the depth values rather than the depth values themselves. Why? Well, depth estimation often struggles with preserving edge information and texture details. By focusing on matching the gradients, this loss directly helps in better capturing the fine details and edges in the depth map. Okay, it ensures that the transitions in depth are smooth. At least it doesn't ensure, but it at least conceptually it can help in that way. So that depth are smooth and consistent, which is vital for, of course, for accurate depth prediction. And then combining these two losses allows the model, at least conceptually, to be more robust and accurate in estimating that depth from monocular images, as it is supposed to handle scale and shift variations and maintain fine details and edges in dense map. Okay. Come back. Okay, the encoder is ResNet 50, initialized with ImageNet decoder. Decoder is initialized randomly. Output head progressively upsamples the predictions with bilinear interpolation to the input resolution. For dataset, they made let's say a meta dataset built on top of Mix5 dataset. Well, that Mix5 dataset is a mixture of 5 different, no, more than 5 different datasets. I forgot how many. Anyway, it's a mixture of many datasets, and it is introduced in this Midas paper. Midas is different model also developed by Intel Labs, and they extend that data set in sense that they added 5 more data set and then called that monster Mix6. Why monster? Well, it contains about 1.4 million images. They used multi-objective optimization, which is a topic on itself. So do I have to say something here also? Okay, they use data augmentation. They trained for 60 epochs. They used batch size 16, and here we see those 3 models. So the DPT base had 112 million parameters. The DPT hybrid had 123 million parameters, and DPT large is really large. Okay, just a brief comparison with Midas, because Midas was best published model at that time with 105 million parameters. They showed 23% improvement on using DPT hybrid and 28% improvement with DPT large. And yeah, I won't go deeper into these details. Okay, just to see some visual comparison here. Here is Midas 6, but in parentheses you see Mix 6. So they, since the Midas was trained on Mix5, they wanted to train Midas on this extensive data set to have better and fair comparison of models. And you can see that those two models give better, at least sharper depth estimation. So here you have some blurry boundaries, and here they are more distinct. Here are even more distinct. Okay, here you can see that Midas gets confused by a tree. This one is not that confused with a tree, and things like that. Okay, let's go to Google Drive now and open DPT. Okay, here we have a DPT pre-trained model downloaded from official GitHub implementation, of course. And here we have, this is a run function also from GitHub, but as I had to tweak some things here in order to work on this collapse setup, which is currently available. So if you like, you can go through this code. It's nothing special here. It's just those boring stuff towards device to CUDA and things like that, to normalize, so pre-process and things like that. So we don't have to care about that right now. Okay. Oh, I don't know what is this. Okay, we need to install some additional dependencies. We cloned the official GitHub repo. We use instructions on from GitHub to copy our downloaded weights to their weights folder, and here we copy our sample images, those 8 images, to the specified folder, and then we call this function run. Well, this function run does prediction under the hood, so everything is done here, and also reading, writing into those files and folders. We don't have to care about that. We just care about results. Okay, and here are results. Okay, here we can see that this DPT model also captured chair boundaries also here up to some extent, but is generally the depth map is, let's say, the edges are sharper. Okay, here is the interesting thing, because it is a random online photo. So you can see that the model actually behaves really well. It doesn't get confused with this shadow of the bridge. It captures bridge nicely. It captures the tree nicely. It is maybe blurry up to some extent here, but generally it does nice job, fine job. Here, for this GPT image, for example, here you can see the object, the building boundaries are captured by the model. Here, the model also captured that those pixels are really far away. Okay, sky should be at least for the model, infinitely far, but that is not the case. But it captured that here we have really far pixels. In here, I was confused by this prediction. So it is really red or yellow. So the model says that this is a really far. And then when I looked closely at the picture, actually you can see that. So you have one sofa and another sofa, and then you have an empty space, and then you have another sofa, and then empty space, and then this bookshelf or some shelf. So yeah, actually it is really far. So the model did even better job that I did. And also it's okay, it is confused by this image, but it's not confused as the previous models were. Okay, come back. And now just to briefly comment this Dino V2 model. This is a state-of-the-art work. The paper is from 2023, and I will reference you and also give you a link for this paper, and I think it's worth reading. For example, I will have some segmentation task for some of school projects, so I'll probably try to use Dino V2 for that segmentation task. Okay, Dino stands for distillation of knowledge with no labels. This is a whole different concept which relates to a method of training models, particularly in computer vision, using self-supervised learning technique. Here, their model, so in self-supervised learning, a model is trained to understand and predict parts of the input data without the need for explicit labeling. The Dino method enables model to learn a rich representation of visual data without relying on labeled data set. Dino V2 is comprehensive extension of that point of view. So Dino V2 is the state-of-the-art work from this year, especially in computer vision tasks like image classification, like image segmentation, and of course depth estimation. Okay, just briefly to explain that paper without any details. So the pre-trained representation that are not specific to any task have become a norm in natural language processing. So the effectiveness of this approach is powered by a large scale pre-training on abundant raw text using unsupervised objects like language modeling or word vector generation. Following this trend in NLP, authors anticipate the emergence of similar foundational models in the field of computer vision. These models are expected to produce visual features that are immediately applicable to any task, whether at the image level, such as image classification, or at the pixel level, like here in depth estimation and also in segmentation. Okay, here in the notes I have some details, but yeah, I will skip that because that is not enough to understand this model. So I will refer you actually to read this paper if you like. Now, for the references, okay, those first three references are the papers that we covered today. The fourth reference is the Dino V2 paper, but also I don't have prepared some column notebook because this Dino model is from 2023 and the GitHub is pretty fresh, so everything works out of the box, and also they have a really nice online demo for this model, so we can look at this. Okay, you have here some comments, some strengths of the models. You have here demos, which will go just in a minute. You have a blog post about this model, of course, paper and GitHub, and also I will recommend you to read the Hugging Face blog on this paper. It is a good one, but sadly it doesn't contain anything about depth estimation. It focuses on classification. So for the demos, okay, I agree. You can upload any image here, and also you have here they offered some images, but I would like to upload the bridge image to see how this model behaves on it. Okay, well, here you can see for example, those grass, or I don't know what is it, those thin objects are also recognized. The model doesn't get confused with these shadows of the bridge. It captures bridge finely. It captures a tree also. It captures, well, let's say, borders of the forest quite nicely. And also, this model has one more feature that others didn't have, and that is that it can give you some perspective of 3D scene here. So if you click on the image and then move your cursor, it gives you some perspective as you were there. So that is an interesting feature. And I would like also to see this weird GPT image. Oops. Oh. Well, yeah, it doesn't get as much confused as other models. It captures the really far pixels here, so this is quite nice. It captures object boundaries. It doesn't get confused with those shadows of the objects here, so it does a fine job. And also you can move it around. Yeah, it's pretty cool. Okay, now I would like to compare all these models in the same notebook, so we can see it side by side. And where did I put that? I think here.
Oh yeah. Okay, here we just load those images. Never, it doesn't matter. It's trivial code. So for the first image, we can compare side by side those predictions. Well, you can say, or I will say that DPT does the best job here in all senses, in object boundaries, in the depth estimation also. Okay. Yeah, also for this picture, you can see now side by side that the DPT does the best job here. And yeah, as we saw, for the bridge image, I mean, if you compare those two, the difference is obvious. Also, I mean, here the difference is obvious, but this one is better than this one, at least visually. Okay, here on GPT images, DPT is also the best one. Yeah, and here, I mean, obviously. I think the other beans gets confused with the shadows, but I'm not sure. Okay. Come back, come back. Okay, do you have something else? Oh, of course, I have I put here my email address, so now I will show you the homework assignment. It's not assignment, it's not to be graded, of course. You can do it if you like, and if you want, you can contact me about your results.
And that's all, folks.
And that's it for the presentation. So we only have to see the homework assignment. It's not assignment, it's just a homework. Here you have a loss function that I will advise you to use. If you like, you can use any other loss function, but you should open with this one and then build upon. Okay, we import some dependencies, never mind. Here, if you store your data set on Google Drive, then you can mount it here. I propose to use NYU dataset. You can find it on Kaggle. Okay, we can. Oh, here. So the data set is structured in two folders. So you have NYU train, and it has its own subfolders with different rooms and things like that. And NYU test has it contains testing images. So you have image and corresponding depth map here. Also, you have some useful thing, and this is those CSV files. So you can read images using these CSV paths written in this CSV file, using those paths written in CSV file. Okay. And then if you use that data set, then you can use these codes. So unzip train, unzip validation, but as you saw, you don't have validation in NYU dataset, so I will recommend you to do it on your own. So you can use a training set and then extract, I don't know, 20% of that data set to use it as a validation for you. Then you can use read this CSV of pets here. Advice, of course, is to shuffle CSV paths. Shuffle paths, not CSV paths. To shuffle paths before training, especially if you're using small buffer size. I will explain this buffer size later on in this code. Okay, shuffle. And then, as I said, NYU doesn't come with separated validation data, so you have to do that on your own. You can load it, then that's shuffled paths. Okay, you can do this sanity check here, so print some paths to see if everything works okay. Then you don't have to worry about processing the path. I did that for you.
Then also I made a TensorFlow dataset. So it essentially creates a dataset where each element is a tuple containing one element from each of the sequences. So we need train image and then train corresponding depth value, and also we need that for validation data as well as for training data. Okay, then here in totalize we just connect train and validation data set that we just made with this process path function. If you want, you can make a data augmentation policy. If you don't, well, you don't need to do that. Here is just some. I mean, you can use this, but you don't have to use it. If you don't use it, then you should comment out this. And then, depending on your GPU RAM you get from Colab, you can reduce a number of pictures that are stored in RAM. How? Well, using this buffer. So a larger buffer size means that the model has more available images to choose random batch. So you can store more images at the GPU at any time. If you it depends on RAM you get from Colab. So generally larger buffer size is a better one, but you are always limited by resources. So you should experiment with that, but keeping in mind that it should be as high as possible. And this prefetch function, it just improves the efficiency of data pipeline, because it prepares or prefetches the next batch of data while the current batch is being used for training. The next batch should be ready to go as soon as the model is done with the current batch, and because we are trying to reduce the idle time of the GPU, so we have faster training. This buffer size parameter just tells TensorFlow how many batches to prefetch. If we say to auto-tune it, then we'll saying him, okay, do the best job as you can. Here, I gave you some example architecture. It is also UNet-like architecture, so like in this first paper, but it's much simpler than that. Of course, feel free to change it, but if you use this this architecture, then you can obtain, for example, those results. So it's not bad, especially if you keep in mind that this model I think has only 300,000 parameters. So it's a really small model, and it does fine job. But maybe you can find a better architecture. I mean, I believe you can. Okay, here is some building block that you might not see before, or you might see, and if you didn't see separable convolution, then I put here a link to learn about it. It essentially reduces number of trainable parameters. It goes through each channel. It goes to each channel, but how can I say that? Let's say it goes to each channel individually. So it doesn't connect channel by channel, and then somehow after that it connects all weights. So you can see in this blog post or something, I forgot. Yeah, it's a blog post here, and you can find, of course, online explanations for separable convolution. It doesn't. It have also its limitation, but its greatest strength is that you don't have many parameters that you need to train. Okay, then here, okay, we load. I chose MobileNet v2. You can actually choose one of those three. Also, you can import another one. You can play around with that. Okay, we don't include top because we don't classify image. We use pre-trained weights, and also we take weights from base model while they are still 14 by 14, because the MobileNet actually goes as low as 7 by 7 at the end of the of the network, but that can be problematic since 7 by 7 is really hard. It is really hard to go from 7 by 7 to the original input shape of the image, and getting a meaningful result. So it is better to cut earlier. Of course, you can cut earlier than that, but then you lose many pre-trained weights. So you need to find a sweet spot here. If you want, okay, we froze all parameters from this model. If you want, you can unfreeze some of them. Here is an example code how you can do that. We had 3 skip connections, so to have a UNet-like architecture. Okay, and then we assemble our model by putting the input as from base model. So this is an encoder. So this is a mobile net, truncated mobile net, and here is our decoder that we made and defined here. Okay. Then okay, you can call model.tačka is in Serbian, model.summary to see how your model looks like, and also here you define what is the learning rate, and also what is, well, first you define the optimizer, and then you define what is learning rate. So it is for you to do that. Here, okay, we compile model, and here you can comment all this, but essentially this is one way of using callbacks. Here you're monitoring validation loss, and if it doesn't decay for this number of epochs, then it will be shrinked by this factor. So this factor should be from 0 to 1, of course. And the mean LR is the minimal learning rate. So how far should this callback go in reducing reducing learning rate? Okay, then we call model.fit to train our model, save that history so we can so you can plot it here. So it is always better to see visually is your model learning or not. And here are some things that you don't have to worry about. I mean, it's just boring code to visualize images. And here I left you just one image from NYU dataset that, and the prediction with that model I made. So, I mean, of course, it's blurry, but you always have to keep in mind that the smallest model we saw today had 42 million parameters. And this model has around 300,000 parameters. So it's a much smaller model. And it also does a fine job here. Okay, you can do evaluation of your model since you have a separate testing data set. Here, I don't think you have to tweak anything. Okay, maybe here just to say what is batch size, but you just can call this few cells, and you will evaluate your model. And I think that's it. So if you have any question, now is the time.
Okay, thank you, Vladimir. It was very interesting tutorial, and thank you everyone for watching. Next tutorial will start at 11:15. Till then, bye.
Bye.